Welcome to this lecture on complex analysis. Today we are going to explore a fascinating and essential topic, the convergence of power series. This is a foundational concept that explains exactly how we can safely add up an infinite number of complex terms without breaking our mathematical machinery. By the end of this video, you will understand how to find the safe zones for these infinite sums. Let us start with a simple, intuitive idea before we look at any equations. Imagine you are walking toward a wall that is exactly 10 meters away. For your first step, you walk half the distance. For your next step, you walk half of the remaining distance. If you keep doing this forever, adding smaller and smaller steps, you will never actually crash through the wall. Instead, the total distance you travel safely adds up to exactly 10 meters. In mathematics, when an infinite sum settles down to a specific finite value like this, we say it converges. If the total explodes toward infinity, it diverges. Now that we understand what convergence is intuitively, let us apply it to complex analysis. A power series is essentially a polynomial that never ends. Because the series goes on forever, we cannot just plug in any random complex number and expect a sensible answer. For some values of our variable, the terms get smaller very quickly, and the infinite sum converges to a neat, finite complex number. For other values, the terms grow out of control, and the sum diverges into mathematical garbage. Our goal is to find the exact safe zone where this infinite math machine works perfectly. This brings us to the mathematical representation of a power series. The formula you see here is the standard form we use in complex analysis. Let us break down what each part means. The symbol Z represents our complex variable, which is the input we want to test. The symbol Z0 is a fixed complex number called the center, acting as the anchor point for our safe zone. The a sub n terms are the coefficients that dictate how big or small each piece will be, and n is the index, counting up to infinity. As the variable z moves further away from the center, the terms grow larger, making it much harder for the series to converge. Because we are working in the flat, two-dimensional complex plane, distance is measured in all directions from that center point. This means our safe zone is not just a simple line segment, but a literal circle drawn on the complex plane. We call this the circle of convergence. Every complex number that lies strictly inside this circle will make the power series converge perfectly. Every complex number outside this circle will make the series diverge and explode. The distance from the center to the edge of this circle is called the radius of convergence, denoted by the capital letter R. Let us visualize this safe zone to make it completely clear. Here we see the complex plane with a real axis and an imaginary axis. The center of our series, Z0, is marked with a point. Around it is a blue circular region of radius R. This blue area is the region of convergence. If you pick any point inside here, the series works perfectly. The red area outside is the region of divergence, where the series breaks down and explodes. The dashed boundary line represents the edge, where convergence is uncertain. To find this exact radius R, we use a powerful mathematical tool called the ratio test. This test looks at how fast the coefficients of our series are shrinking or growing as we move further down the infinite list. By comparing one coefficient to the very next one in line, we can predict the behavior of the entire infinite series. We do this by setting up a limit as n approaches infinity, comparing the absolute value of the next coefficient to the current one. If this limit, L, is a large number, the terms are not shrinking fast enough. If L is a small number, they are shrinking rapidly. Once we find that limit L, calculating the radius of convergence is incredibly simple. This formula tells us that the radius R is just the exact reciprocal of L. If L is a large number, r becomes very small, giving us a tiny, restrictive safe zone. If L is a tiny fraction, r becomes massive. There are two special extreme cases to remember. If L is exactly 0, r becomes infinity, meaning the series converges for every single complex number in the universe. Conversely, if L is infinity, r becomes 0, meaning the series is completely useless except at the exact center point. Before we move on, let us see this with a concrete example. We will find the radius of convergence for the complex exponential series, which is z to the power of n divided by n factorial. Our first step is to identify the coefficient from the series. Since the center is just 0 here, the variable part is simply z to the power of n, leaving our coefficient as 1 over n factorial. Next, we find the coefficient for the very next term in the series by simply replacing every instance of n with n plus 1. Continuing with our example, we now apply the ratio test. We set up the limit of the absolute value of the new coefficient divided by the old coefficient. To simplify this complex fraction, we multiply the top fraction by the reciprocal of the bottom fraction. Remember that n plus 1 factorial means multiplying a number by all integers smaller than it. So it is just n plus 1 multiplied by n factorial. The n factorial terms on the top and bottom will cancel each other out perfectly, leaving us with a much simpler fraction. Now we evaluate the limit. As n grows larger and larger toward infinity, the denominator of our fraction becomes infinitely large. 1 divided by an infinitely large number approaches 0, so our limit L equals 0. Finally, we find the radius of convergence by taking the reciprocal of L. Dividing 1 by 0 in the context of limits gives us infinity. Because the radius is infinity, the safe zone is infinitely large. This means you can plug absolutely any complex number into the exponential series and it will always successfully converge to a finite answer. Now let us look at a slightly more restrictive scenario. We are given a power series where the variable part is z minus 2i and it is divided by 3 to the power of n. First we look at the variable part, which tells us that the center of our series is the imaginary number 2i. Next, we extract the coefficient by ignoring the variable part entirely, giving us 1 over 3 to the power of n. We then find the next coefficient in the sequence by replacing n with n plus 1. We continue by setting up the ratio test, dividing the new coefficient by the old one inside an absolute value. We simplify the fraction by multiplying by the reciprocal. Using the standard rules of exponents, 3 to the power of n plus 1 is exactly the same as 3 to the power of n multiplied by 3. The 3 to the power of n terms on the top and bottom cancel out completely. Because all the n variables cancelled out, we are left with the limit of a constant, which is very easy to evaluate. The limit of a constant is just the constant itself, so our limit L is exactly 1/3. To find the radius of convergence R, we take the reciprocal of L. The reciprocal of 1/3 is 3. This result tells us that our safe zone is a circle with a radius of exactly 3 units. Because the center of our series is pinned at 2i, the series will only converge for complex numbers whose distance from 2i is strictly less than 3. Anything outside this specific circle will explode to infinity. You might be wondering why we care so much about finding these safe zones. Understanding the convergence of power series is absolutely critical in the real world, especially in computer science and electrical engineering. Computers and calculators do not actually know how to compute sine waves or complex exponentials natively. Instead, they approximate these functions using power series. If a software engineer programs a computer to use a series outside its radius of convergence, the computer adds up exploding numbers, resulting in a catastrophic overflow error or completely garbage data. Let us wrap up what we have learned today. A power series is an infinite polynomial used to represent complex functions. Convergence is the mathematical guarantee that adding up these infinite pieces results in a sensible finite number. This safe zone always forms a perfect circle in the complex plane, centered at a specific point. By using the ratio test on the coefficients, we can easily calculate the radius of the circle and know exactly where our mathematical tools are safe to use. You now have a solid understanding of convergence.